Okay, in this word problem, it's a business application. We have this price function. The estimated demand for steel is satisfied by this equation here. And the total cost of producing X units of steel is this. Okay, the quantity X is measured in millions of tons, so that's important. And the price and cost are measured in millions of dollars. Okay, oftentimes I leave out units because it does kind of jumble up the work. However, certain people are very picky that it's shown all the way through. Oftentimes you could kind of see in the final answer if it makes sense or not, and that's why I leave them off. But on that note, I took a chemistry course recently, and units saved me. I mean, without writing the units, some of the problems I couldn't even do. Right. Okay, so we have these two old formulas, R of X equals X times P, right? The price times the quantity sold or produced, and the profit is revenue minus the cost. So combining both of those things, we are trying to maximize profits. Oops, I put a R. We're trying to maximize the profit, which means we're going to need that derivative, right? The revenue is X times P. Well, we have P, so we just need X multiplied by that P, which was given. Okay, so the demand, the price is a function in itself. So there's now revenue. Subtract the cost, which that function is given. I think, we're trying to maximize it. We're going to need derivative. I kind of think let's just distribute and combine like terms. I think it would be easier. So the profit is 256x minus 50x squared minus 182 minus 56x. Okay, so really only these two combine. So we know the profit then is equal to a negative 50x squared plus 200x minus 182. That's what we're trying to maximize. Let's do derivative. And of course, we're setting that equal to 0. So negative 100x plus 200, and then derivative negative 182 is 0. Solving for x, 100x equals 200, x is 2. Let's verify really quick that that is a max. That's really easy in this one. The second derivative is negative 100. So negative second derivative concave down, which tells me max. Okay, so we're good there. Piggybacking off the last section's endpoints. Well, X is the units of steel, right, produced. Producing 0 units obviously will not be a max. And there is no bound here, right? There's no, for instance, does it say there's only, up to 10 million tons or whatever available that could be mined or produced or whatever's going on here. There's no other restrictions. There's no other bounds. So we have to assume for this function that we don't need to check endpoints, and that is the absolute max there. One other thing to point out, X is measured in millions of tons. So 2 million tons, will maximize profit. Now there's one more piece of this question though, right? The level of production and the corresponding price. This is the production. They're going to produce 2 million tons of 2 million tons of steel to maximize the profit. At a price, well, that's easy because now that we have 2, right, they give us the function 256 minus 50x. So minus 50 times 2 is 156. Now, this is in millions, right? Because it tells us it's measured in millions of dollars, the price and the total cost. So units here, $156 million. We could even go further and make sure all of these units are correct, but 156 million per ton